finished my defense last week, so having a little bit of more downtime now. And in my PhD study, I've been mainly focusing on how we guarantee safety for these kind of advanced autonomous systems, either in the robotics application or also in this aviation industry, like the autonomous aerial vehicle. So that will be the focus of today's talk. And the main kind of like the main high-level objective I want to deliver is how we can leverage both the AI and control theory to provide safety framework for this new generation autonomous systems. So as a person who studied mechanical engineering, control theory, and robotics, my lifelong vision is to build autonomous machines that really can help the human society. And of course, there are many, research challenges and like many research open research problems to achieve this vision. But one of the main challenges that I strongly resonated with when I started my PhD was how we can provide formal safety guarantee for such complex autonomous machines. And these days, as we see in a variety of domain that this kind of autonomy scale to the societal level. And when we see this large-scale autonomy, even a slight chance of safety violation can lead to catastrophic results, such as the human casualties, as we have already experienced in the self-driving industry or in the aviation industry. Violation of such safety is not only detrimental for the human society, but apparently such guarantee of safety is really the foundation for achieving the sustainable and reliable operation of such autonomous machines. Therefore, this has been the main focus of my PhD study. And more specifically, I aimed to develop generalizable safety frameworks that applies across various domains like robotics, including autonomous trucks, legged robots, manipulator, and also the aviation autonomy, including these autonomous aerial vehicles. And in today's talk, I will like to mainly focus on some of my works, focus on application for this air mobility system or this aviation autonomy. Mainly because this was the most serious kind of applications I investigated through this collaboration with NASA, MIT, and also Joby Aviation, which is one of the leading air taxi companies in the Silicon Valley. So now let's jump into what I want to do by using the framework in control theory and data and learning. So control theory is really nice because it provides this assurance principle that can be used to formally guarantee safety of such system. However, these guarantees are typically very much based on accurate characterization of the system's model. And when we lack such model, as we will see later in the talk, such guarantee can break down. So basically, how can we overcome such limitations of model-based analysis in control theory, which has been established in the past decades, by bringing in the framework in the machine learning or like data-driven approaches. So to deal with these diverse and uncertain situations and dynamics of the system. So this is kind of the main paradigm I'm trying to push forward to provide this generalizable safety framework for such societal scale autonomy. Now let's look into the specific, various decision makings happening in this advanced air mobility system. So advanced air mobility system is, to start with, it's just a new kind of jargon in the aviation community, referring to all these new generation aerial vehicles and also the service based on those vehicles, like the drone deliveries or the air taxi services. And these advanced air mobility systems, there are various decisions that has to be made to operate such services or system, starting from the operation level, such as route schedules of the vehicle, all the way down to the vehicle level, decisions like the attitude control of the robot of the vehicle or the battery management of the vehicle. So among these various decisions we have to make at various levels of this system, there also are various safety challenges. And today we'll mainly focus on the safety challenges at the vehicle level and the trajectory level. So at the vehicle level, one of the main kind of novel challenges for this system is that a lot of the new generation these aerial vehicle go through the so-called flight mode transition between this kind of hover mode or the helicopter mode and this cruise mode or the airplane mode. And during this transition is when we have a lot of uncertainty due to this uncertain, hard to model aerodynamics. The vehicles are also much more vulnerable to stall condition, and there is a precarious balance that has to be met between the lift from the rotors and the lift from the wing. So all these various challenges make this vehicle really susceptible to the loss of control during this flight mode transition, which can actually lead to accidents these accidents have actually happened in the past during the actual operation of such vertical takeoff and landing vehicle or the flight test program of the new generation vehicles. So how do we address this novel and uncertain dynamics underlying this mode transition is one of the main safety challenge for this vehicle. And today, in the first part of the talk, I'll show you how we can construct a verified safety region of the robots or the system state directly from the trajectory data. Moving to a different challenge at the different level, which is at the operation and trajectory level. There are also an emerging challenge due to the increasing volume of the traffic of these aerial vehicles. Reports stemming from 2023 has raised concern about manual air traffic controller not being able to handle the rising volume of this air traffic demand. And such understaffed issue is actually pointed out as one of the issues that contributed to the recent tragic accident that happened in the Washington, D.C. So as you can see, the aviation community has a really strong need to innovate their existing air traffic management system to the autonomous level or the semi-autonomous level. And in order to achieve this new generation ATM or the air traffic management, people are investigating how we can leverage or use learning-based methods such as the multi-agent reinforcement learning to do this. However, the main limitation of such learning-based paradigm is that they don't have a rigorous safety guarantee. So in the second part of my talk, I'll show you how we can actually bring in control theoretic work and combine it with this multi-agent RL to not only achieve the safe operation of this vehicle, but also a more efficient operation of this vehicle traffic management. So the outline of my talk will start with a more specific background for safety problems and also go through these two works one by one. And then I'll finish the talk with the outlook and the exciting future work directions. So let's go into the background. So now let's kind of formally think about why the safety problem is hard and what are the problems we want to solve when we want to guarantee safety for such systems. So consider this cartoon diagram here where this air taxi is trying to avoid this building. So the safety specification is given as this vehicle having to avoid the collision with the building. But given this safety specification, it's not straightforward to directly impose this condition because within our constraint region, although the current robot state might be within our constraint region or within our safety region, no matter what the vehicle does with its control action, there are some states in this constraint region where the vehicle will inevitably lead to this failure state. So the first fundamental problem for safety is effectively ruling out such failure region where we cannot do anything about to prevent the safety violation, and coming up with this subset within our constraint region that is dynamically feasible for the robot to stay within. So finding such subset within our constraint is the first fundamental problem. And the second problem will be then how we effectively guarantee that the robot will stay only within this subset or the dynamically feasible state set. So, among many control actions the robot wants to take, how we verify that whether the action is safe or not, and then if it's unsafe, how do we filter such a potentially unsafe action with a safe action will be the second problem, constituting these fundamental problems. So if we can solve both problems, then basically we can kind of guarantee that the vehicle will be staying within our constraint set. To solve this problem, there's this concept called certificate functions for safety. And certificate functions combines the desired safety information, safety constraint information with the reasoning of the long-term effect of the dynamics, and combine them into a single scalar function whose zero level, the level of this function, provides or represents the dynamically feasible safe set. And its gradient can be used to evaluate whether a control action is safe or not. So if we can design such a scalar function, this certificate function, then we can use such certificate functions both to represent our safe set and also to evaluate our safe control input. So this is why this concept is really powerful. The main challenge is coming from how we compute or design such certificate functions. And next, I'll review how we can use the so-called Hamilton-Jacobi reachability framework to compute such a certificate function. So consider the robot here, that wants to stay within this box region. This is a very simplified toy example. And now the robot is subjected to its dynamics given by this differential equation, F, where X represents the robot state and U represents the control action we can take. So depending on our control action, if we take U1, then our state trajectory will stay within our constraint region, which will be safe. And if we choose a different control U2, then it might lead the robot state to the failure region. Now, as I said earlier, there are some states within this constraint region where no matter what you do with your control, it will inevitably exit this constraint region. So we want to rule out all the states where there's no such control to guarantee safety. Then the remaining part will be our maximal safe set within our constraint region, where there is at least one control signal that guarantees the robot to stay within this set. And now this reachability's main idea is to formulate the solution of this problem as an optimal control problem. So we will consider the cost function here, which measures the closest distance to our failure region. So G is a distance-like function to our boundary of the failure region. And if we measure the closest distance over the time horizon of our trajectory, then if this value is non-negative, so if this value is positive, that basically means that our trajectory is within our constraint, so being safe. So the objective for the safety could be just to maximize this margin, right? So our objective of the control will be maximizing this cost function. And now this becomes the optimal control problem. And this value function captures this cost function of the optimal control problem. And because, as I said, this margin, if this margin is non-negative, then we are safe. So if our value function is non-negative, then that characterizes our maximal safe set. That would look like this. And we can evaluate the dynamic programming principle underlying this value function and come up with this Hamilton-Jacobi partial differential equation. So this is a PDE, and if we can numerically or solve this PDE, then basically we can compute this value function. And once we compute this value function, then basically we have this safe set constructed. So all we have to do now is solve this PDE. But in the beginning, I mentioned that the robot is subjected to its dynamics. So where is the dynamics in this equation? So the dynamics is within this H term, which is called the Hamiltonian of the Hamilton-Jacobi PDE. So Hamiltonian looks like this, and this P is basically representing the gradient vector of the value function. The more important thing here is that it is multiplied with the dynamics here. So this is where the information of our dynamics is used. And in order to evaluate this Hamiltonian, we have to come up with the model for these dynamics. So then the main challenge for this uncertain dynamical systems comes from how can we solve this Hamiltonian if this dynamics is unknown? Can we do this Hamilton-Jacobi reachability using not the explicit model of the dynamics, but by using the trajectory data? By the way, I'll pause every now and then to get some clarifying questions. So I'll pause here now. Is there any questions so far? So now, given this kind of background that we need to evaluate this Hamiltonian, and when we evaluate this Hamiltonian, we need this access to this dynamics. Can you use data to approximately solve this problem? Will be the motivating question. And actually, the practical motivation again comes from my collaboration with Joby or NASA on kind of guaranteeing the safety framework for their air taxi vehicles. So NASA has this nice tilt-wing vehicle that is kind of a concept vehicle that is used to evaluate, various operations of the air mobility in simulations. And Joby has a similar vehicle. It doesn't tilt the wing, but it tilts the rotor, called the S4. And for this new generation vertical takeoff and landing vehicle, loss of control during this kind of flight mode transition is the main challenge for safety. And if we kind of think about this problem, by connecting to this concept of Hamiltonian, it is really challenging because this dynamics of this air taxi vehicle, it does change. It keeps changing as we have different configuration of the vehicle. And also the underlying aerodynamics is really hard to model or even simulate with the advanced CFD tool because of the coupled interaction between the rotors or also between the rotor and the airframe of the vehicle. This really results, even when we can simulate such kind of dynamics, usually they lack a closed form mathematical model. So when we want to solve the math underlying this Hamiltonian, we might prefer very concrete mathematical equations, but we don't have such equations for this vehicle. And finally, even when we can come up with an approximate equation, usually they lack specific structures such as the F being affine in the control input to make this optimization problem easier. So all these challenges make this safety analysis really, really challenging. However, one thing we have again is that we have extensive flight test data. When we run experiments from this vehicle, we collect really these air taxi companies or NASA collects like tons of data of the vehicle trajectory. So can we leverage those data to solve this problem? It becomes the practical motivation of why we want to bring in data for developing this safety framework. So now that leads to this first kind of research component, which is the so-called data-driven Hamiltonian framework that we recently submitted to CDC and we published it to arXiv. This is in collaboration with Chris Strong and Naman Cho. Chris is a PhD student in our group at UC Berkeley, and Naman Cho is a professor at Cranfield University in UK. So going back to this reachability problem, and that in order to solve this safety problem, we have to solve this Hamiltonian. Can we directly solve this with using the trajectory data is the main motivating question for this work. And to tackle this with data, we will first come up with an abstraction that abstract away our dynamics equation. So instead of considering this differential equation where we have to operate with this explicit F, our dynamics, we'll abstract away F by substituting F with V, the state velocity. So it represents the velocity in our state space. And now we have this valid velocity bound, basically all possible F, depending on what control action you choose. When we make such abstraction, our Hamiltonian originally under this representation can also change to this form, where F again is replaced with V. But the nice thing about this now is that we have a linear objective function for our optimization problem. The unknown kind of nonlinear objective function, which was F, is now kind of going underneath our decision domain, which is large F here, the velocity bound. So basically what I did is changing the decision variable of our optimization from control variable to this state velocity variable. Based on this abstraction now, I'm ready to present the main concept of the data-driven Hamiltonian. So in the data-driven Hamiltonian, this is a kind of cartoon diagram of the state space and the state velocity space, where the vertical axis is the state and this horizontal dimension is the velocity. And depending on where our state is, we have various velocity bound. And if we take the top-down view of this velocity bound, it will look like this, which is unknown for us because we don't have the dynamics equation. But and we want to evaluate, given the objective direction P, we want to evaluate what is the maximal we can achieve. So in this case, this point, red point here, will be kind of the optimal we want to find. Now we'll consider that a data set is given to us, which is a collection of the state input, the state variable, the control input, and the velocity variable evaluated at various point of the trajectories. So trajectories collected from our flight test experiments. And we'll show one trajectory in this velocity and state space that would go through like this. So we can sample various data points on this trajectory given by the state and velocity tuple. And from the top-down view, these velocities looks like this. And basically, these are kind of the information we roughly have to evaluate how the vector field bound, sorry, the velocity bound would look like. But the critical thing to note here is that each velocity measurement in our data set is not exactly measured at our current state x. It is measured at a different state. So then we'll use this Lipschitz property of the dynamics, which usually hold for a variety of a dynamical system, to project the data at these various states to the current state with the associated uncertainty with each data. So what I mean by that is within this uncertainty set, we know that a true velocity evaluated at our current state under this control input U1 will be within this uncertainty set. So then now we're ready to present this concept data-driven Hamiltonian. So this looks a little bit scary, but if I parse the equation, so the mean term basically reason about the worst case realization of the uncertainty, basically meaning that given the objective function, what would be the worst case realization of the ground truth velocity associated with each data point. And once we reason about this worst case uncertainty, then we will pick the maximum that can achieve with respect to our objective direction, which would be this point here. And the nice thing now about this new formulation is that no matter whether the underlying optimization problem is non-convex or not, it's not unknown, we can solve this. This formulation itself is a convex optimization, which has actually a closed form solution. So we can evaluate this data-driven Hamiltonian really fast. And actually, this can also be parallelized by using GPUs. So the evaluation can be done really, really fast. And the final solution we get, which is H hat here, is always guaranteed to be the under approximation of the ground truth Hamiltonian, as you can see in this cartoon diagram. And this is the main theoretical property of our formulation. And why is this important is because it results in a guaranteed under approximation of the value function as well when we use the data-driven Hamiltonian in our Hamilton-Jacobi reachability computation. And finally, as a result of that, we also have a guaranteed inner approximation of the ground truth maximal safe set. So when we think about the safety analysis, it's always nicer to estimate this safe set with more conservatism. That's why we really care about this inner approximation guarantee. So in summary, with this new data-driven Hamiltonian, we can combine this model-based framework, which was this Hamilton-Jacobi reachability framework, with these data-driven approaches. And the key idea enabling this without explicitly modeling the underlying vehicle dynamics is this effective abstraction that uses the state velocity representation. And finally, this enables us to achieve inner approximation estimation of the ground truth safe set. So with that, now I will actually show how this works in the real example. Before that, any questions on the theory part? Okay, I know that this can be a little bit intense for you, so yeah, please, yeah.
There's a one who raised the hands. Please go ahead. Yeah, Kim Yunsa, please ask. Go ahead.
Can you hear me?
Yep.
You said Vito has more stall risk, but I have a little less understanding about this. Is this the problem when changing Hilbert form to
Yeah, exactly.
Okay.
Yeah, because the vehicle has a much bigger angle of attack when they do such transition.
Okay, thank you.
Yeah, thanks. Okay, any other questions? if not, I would like to maybe move on to the example now. So we will consider this XC15 vertical takeoff and landing vehicle for the example. And this is a quite ancient model from 1980s, which is almost the ancestor of all existing vertical takeoff and landing vehicle in the market. And why we consider this kind of old model is because this is almost the only model that we have whose mathematical models are known for a public. So there's a white paper showing all the flight test data of this vehicle and also the mathematical model of this vehicle so that we can use the mathematical model to validate the theory guarantee we have with the data-driven Hamiltonian. So this vehicle model goes through the flight mode transition from this hover mode to the cruise mode, where you can see that this rotor changes its configuration from vertical to this horizontal mode. And we'll consider the longitudinal dynamics of the vehicle, meaning the forward kind of motion of the vehicle. So the vehicle state is represented with its airspeed, flight path angle, and the rotor tilt angle. The rotor tilt angle from 0 degree to 90 degree. And we have this equation of motion underlying these dynamics. The challenging part of this equation of motion, again, is this aerodynamics term, the lift term and the drag term, that is actually quite nonlinear. And it also changes with respect to the rotor configuration. So, and also we'll think about how one would practically use this framework. So this data, earlier when I presented this data-driven Hamiltonian, I basically said, oh, there's this data set given to us. But actually, data set usually is not given to us. We have to collect such data, right? So another important aspect of the safety problem is, can we collect such data safely? So in order to do that, we also come up with this framework that does this iterative safe set expansion. So we initially run our experiments from a very, very conservative safe set, like vehicle just staying very, very near the hover configuration, right? Before, like, if we don't know even how we can fly the vehicle and hover it, then we would probably not start our flight experiment. So this is the first assumption, that when we start our flight experiment, we will at least know that vehicle can hover. So vehicles start from this very conservative safe set, and then we will collect data within this conservative safe set, and then we add that to our data set, and then we update our value function, the safety value function, based on our data-driven Hamiltonian, and then after this update, we will have a slightly bigger safe set. And then we can do this procedure over and again so that we can expand the safe set while doing the data collection safely. So in this example, the target set is designed as this trim corridor between the hover configuration and the cruise configuration. So this is a collection of the equilibrium point of the vehicle connecting from the hover configuration to the cruise configuration. So that if the vehicle can return to any of the point in this yellow set, then basically we can guarantee safety of the flight mode transition. So you can see that in the hover configuration, the tilt angle is 90 degree and the velocity is near 0, so it's near hover. And near the cruise configuration, the tilt angle is 0, so it's hover configuration, and the velocity is around 80 meter per second. So it's an airplane mode where we have this forward airspace. And in each iteration, we'll collect 20 trajectories whose initial states are kind of indicated by these red dots. And then I'll show you how this expansion goes. So in each iteration, we run these experiments. We update our safe set. Our safe set becomes bigger, so then we can run new experiments, and we can keep doing this over and over again. After 20 iterations, we'll see like this result here. Yeah. And if you take a closer look at one iteration, so here we have various trajectories we experimented in this iteration. And some of them are near this near hover configuration with a large variation in the vertical airspeed. Some experiments are done in the mid-transition. Some other experiments are done in the cruise configuration. So basically, you can see that we collect a variety of data to expand the safe set in diverse direction in our state space. And after 20 iterations, this is the final result we get. So the blue one is the data-driven safe set we compute from the DDH, the data-driven Hamiltonian. And compared to the true ground truth SafeSat, we can compute from the known mathematical model of this vehicle. We can actually see that the computed data-driven SafeSat is the actual under approximation of the ground truth SafeSat. And you can also see that the volume recovered is quite significant compared to the ground truth. So this is the main result. And I want to finally conclude with some of the existing work, comparison to the existing work, why this new work is a little bit better in terms of generalizability. So an alternative approach on the left can be, when given this uncertain dynamics, we can maybe first come up with the best approximate model of these dynamics. But then there's a gap between this our nominal model and the underlying true dynamics. If we don't address those gaps, that gap can break down our safety guarantee. So what people have done is coming up with this data-driven model, this learning-based component that evaluates how this gap between F and F tilde can affect our safety, and use that in our computation of the safety circuit functions or reachable analysis, and then also designing our safety constraint. Whereas this approach actually basically circumvent the need to come up with this nominal model, which really requires a lot of domain expertise and extensive kind of modeling efforts. And also, we don't need to come up with a separate component for coming up with this error. So we use the data directly in our SafeSat computation, not to capture the error between our model and our dynamics. So this is why we call this approach direct. And since we circumvent a lot of the process that requires a lot of extensive efforts, that's why I believe that this new direct approach can minimize such extensive efforts, engineering, and enable a more generalizable framework for data-driven safety analysis. So that concludes the first part, technical part of my talk. And the second part will be how we use such safety framework for automating the air traffic management. This is done in collaboration with Professor Hamza Balakrishnan's groups at MIT, also with Jingxi and Gabi at UC Berkeley. And this paper just got accepted to RSS 2025. And we'll publish this work probably sometime end of April on arXiv.
There was a question. There was a question on the chat window.
Yeah, I'm seeing the question now. How can you expand the SafeSat while starting in a safe initial configuration and also having a conservative SafeSat noted by max in epsilon ball? In other words, how can you encourage exploration while online? Yeah, that is a very, very good question. So actually very critical question for this safe exploration problem, right? Because we always want to make sure that the vehicle stays within the previous verified SafeSat, but we want to do more exploration. So this is like a pre-verified SafeSat from our previous iteration. And then if we don't carefully design our experiment, then such exploration is not done properly. And then maybe we will not be able to expand the SafeSat in our next iteration. So in this work, actually, we kind of tested various things for exploration. For example, all this trajectory, I think, have some random perturbation in the control signal so that we can have various excitation of our dynamics. But it's also very relevant to, in the learning kind of literature, something called regret, right? So depending on how efficient your exploration is, you can achieve minimal regret. But all those questions relevant to all those questions while doing the exploration subjected to the safety constraints, I think it's quite open problem. So analyzing such regret or how efficient exploration is, those are all I think the open questions that I want to investigate on top of this work as a future work direction. Did that clarify your question? Okay, thanks. Any other questions before I move on to the second part? Okay, so then now I'll move on to this air traffic management part. So the air traffic management part, as you know, like that, the aviation community, of course, already have a lot of layers for safety. Starting from this airspace separation, centralized manual air traffic control, and then protocols that, when two vehicles actually engage, what do they do? One vehicle should always turn right, things like that. And finally, the imminent collision avoidance module, something like the TCAS or ACAS, that are already on board on these commercial airliners. But the new challenge for this advanced air mobility era is that, for example, the NASA and FAA has announced that they will open up the market for private market for services for this air mobility, such as the air traffic operation, so that this air traffic operation will be decentralized. And since we'll have a much higher volume of the vehicle, within the same airspace, there will be multiple vehicles engaging with each other. And these protocols or collision avoidance modules are built around important assumption that at most two vehicles engage in the confliction simultaneously. So what happens if there's a third agent? It's an open question. Of course, we haven't seen any accidents like this yet, but this is definitely the main concern for this high density air traffic operation. And if all these layers of safety fail, we will eventually see a lot of critical accidents. So the main motivation for this project is the need for safe decentralized autonomy that can work as a final layer for safety when all of these upper level safety modules fails. As a quick background, maybe I'll actually skip this slide. Maybe it's too technical, but as I showed you earlier, we can use the reachability to evaluate what are the safe sets when the vehicle engage with each other. So here, I use this reachability computation to evaluate the safety boundary between a pair of vehicles. So consider this vehicle as your vehicle right now, and given these two other vehicles, near you, this cyan level set is the boundary of the unsafe region that our Avigo vehicles shouldn't enter with respect to the cyan vehicle, and the blue curve is also the unsafe boundary that the Ego agent shouldn't enter to avoid collision, right? So then the reachability says we are outside this failure region with respect to these other vehicles. So then, do you think this current configuration is safe for this three vehicle, or would there be any issue? Do you think it's safe? So I actually, when I present this result, I get a kind of feedback that this is outside the safe sets, but this looks unsafe. So actually, that's correct. That when we run the simulation of this three agent interaction, we can actually see that the vehicle enters the failure region in terms of the relative distance. So this is the distance that is set as the near collision distance. And you can see that if even when we execute our optimal control for safety, the vehicle relative distance becomes lower than this near collision distance. So why is it the case? The main challenge for this multi-agent safety problem is that the issue of leaky corner, which means that the intersection of the safe set of individual constraint is not the safe set of the intersection of the constraints, meaning that there is some region within this intersection of the safe set that if I want to satisfy one constraint, I have to sacrifice the other constraint. So satisfying both constraints at the same time, to do that, we have to actually solve the safe set for the entire dynamics again, for the three agent dynamics again. And maybe we could do that for this particular problem. But the main challenge is, can you do that for any possible combinatorial, combinatorial cases of the multi-agent interaction? So that is why it's really, really challenging to guarantee safety for the this high density multi-agent interaction. And for us, the main idea of this project is actually to define the new region called the potential conflict region, where within this potential conflict region, if there's more than two vehicles within this region, this leaky corner issue can arise. and safety guarantee for all agents might not hold anymore. So for example, one agent can enter this region. That's fine, because these two agents can actively, engage to avoid collision from each other. But then if there's this third agent that enters this potential conflict region, then now resolving the collision for all three agents might not be possible. So this nicer thing for the third agent to do is basically avoid entering this conflict region when they see already more than one vehicle within this region. So then it can avoid the leaky corner issue. And the nice thing about this definition is actually we can use this reachability computation we did earlier to evaluate what is the range of this potential conflict region. And now after that, we can kind of inform our multi-agent RL policy so that the agent actually learns how to avoid such region. So in our layered safety framework for multi-agent RL, each agent makes their decisions based on the local observation they perceive within their observation range. So in this case, they perceive that they have these three other agents around them, and then they want to get to this sequence of waypoint. And we use graphical neural network to embed this local information into an embedding vector. And then more multi-agent RL policy is evaluated based on that embedded vector. The important thing here is that when they make such decisions, there's a reward term that penalizes agent from entering such potential conflict region. So that is a kind of soft safety informing kind of framework for the multi-agent RL. And then following that are the hard kind of constraint. So we evaluate again this CBVF value or the reachability value function value for each pair of agent. And the value with the minimum value or the worst value is basically the pair with the highest collision risk at the moment. So then we apply the reachability-based safety filtering or the barrier function-based safety filtering for such particular pair of vehicle. So by doing so, there's this hierarchy of safety imposing each layer, right? Starting from the soft safety that inform the agent to avoid such potential conflict region, all the way down to this active engagement for collision avoidance. So this is our framework. As I said earlier, if we do this for a variety of vehicle dynamics, such as the quadrotor or the air taxi vehicle, we can compute both the safe set, the value function for the safety filtering, and also the potential conflict region. And then we use this computation to design such safety framework all the way from the MAR to all the way down to the safety filter. Now, this is how it goes in the hardware experiments. So here are 3 drones, and they have to go through these 2 waypoints to get to their landing location. And if they miss this waypoint, they have to go through this waypoint again, because this is a virtual air corridor for this vehicle. And notice the behavior of the third agent. So in the first case, where we haven't informed the multi-agent RL policy in the training with this knowledge of the potential conflict region, then you can see that all the agent attempts to merge to the corridor at the same time, and then the third agent is blocked by the other 2 agents. So then it has to go all the way back to the air corridor again to get to its landing location, which makes this navigation really inefficient. Whereas now, if we inform our multi-agent RL in the training with the issue of this potential conflict, you will see that the third agent actually waits until the first 2 agents pass through the air corridor, and then it follows them. So the entire navigation is done in a much more efficient manner. And then now we extend this study to a larger scale simulation study of the air taxi operation. And here, I want to clarify that here the vehicle dynamics is quadrotor, whereas in the next simulation, I'll show you the vehicle dynamics is a more wingborne flight. The main distinction between these quadrotor dynamics and the wingborne flight is that for air taxi, they cannot stop at their current configuration. So then if they want to avoid collision, they have to, like turn. use the turning mechanism to avoid safety, which makes the safety guarantee much harder for this air taxi vehicle. So in this simulation scenario, I'm simulating 8 vehicles starting from various locations in the Bay Area, merging to San Francisco. So this is a hypothetical scenario. In the morning time, everyone wants to get to their workplace using the air taxi. And all these vehicles merge to this air corridor to converge to San Francisco. Now, this is what happens with the safety blind multi-agent rail that doesn't know the issue of potential conflict. As you can see, as we activate this safety filtering mechanism, a lot of the operation becomes really, really inefficient due to this active kind of collision avoidance maneuver. And you can see that the entire avoidance kind of behavior are really quite entangled from each other because a lot of the agents try to avoid each other at the same time. We compare that to our new results. So this is the policy that is informed about the issue of potential conflict. You can see that the entire navigation is done in a much more efficient manner. And we can evaluate the average travel time. The travel time is decreased significantly, and our collision rate is also decreased a lot. One thing, finally, I want to note here is that this is kind of like a worst case simulation because we are not imposing any higher level rules or structures. There's no centralized decision, there's no rules. So this would happen in reality when all the existing infrastructure goes down and the vehicle has to make decisions only on its local observations. So in a more practical setting, I believe that the near collision rate actually can be much, much lower to the kind of standard that the aviation community wants. And still this framework can serve as the last layer for safety. So the summary of this second part of my work is that the main issue for this multi-agent safety is this conflicting constraints, the leaky corner issue. And the key idea for informing more with this safety in our work was treating this potential conflict as a soft constraint and allowing the MAR policy to know about this issue by imposing a penalty signal in their reward function design. Maybe before I wrap up the talk, any questions specifically for the second part of the talk? Okay, then I'll happy to take more questions after I wrap up my talk. So in my today's talk, I mainly showed 2 challenges for safety. One one with respect to the uncertainty dynamics for the air taxi vehicles, and the other the uncertainty arising from the multi-agent interaction. But there are a variety of uncertainty source in the safe decision-making problems for real-world autonomy, and all these uncertainty sources are still active research challenges that I want to solve in my ongoing work and my future work. But in a broader view, specifically for the aviation autonomy, so going back to this hierarchical diagram of all the decisions in this air mobility system, starting from the operational level, the vehicle level, my main worry is that as this operation scales more, involving much more vehicle, much more operation parties, much more service providers and whatnot, all the various sources of uncertainty in the operation level, in the vehicle level, they will start to interact with each other. And uncertainty in one decision layer will have a cascading effect for the decisions in the other layer. Like the demand uncertainty will have a high impact on how many agents will be interacting with each other, and vice versa. Like the vehicle health condition can also have a upstream effect to how we want to operate this vehicle to achieve better safety and efficiency. So my main, I think the most exciting research question for the new generation aviation is how we deal with this tight kind of coupling between the decisions of these layers. And as you can see, there are all sorts of data we can leverage. So, like these flight companies, airliners, airport, they all collect a bunch of data, at the operation level, at the trajectory level, and at the vehicle dynamics level. And probably by, bringing in these new, techniques and frameworks in AI, we'll be able to achieve a better decision-making paradigm for this aviation autonomy. And I believe that in order to, rigorously guarantee safety, control theory will also have a crucial role, as I showed in some of the works I presented today. So my hope is I can show much more practical impact by combining the tools in AI and control theory for the next generation safe aviation autonomy. So with that, I would like to end my talk. Thank you for listening to my talk, and I'm happy to take more questions.
So there was already, thank you for your presentation. There are already questions on the, I think, the chat window. Please ask questions.
Yeah.
Just
maybe I can start with the questions in the chat then. So question from Jingu. In the real world, there are various types of vehicles floating in the air at the same time, including military, commercial vehicles, and personal helicopters. I'm curious, if we were to implement your idea, how could we provide safety signals across such a diverse range of platforms? That's a really good question. So a lot of the safety analysis I've done today are specific to the dynamics of each vehicle, right? So if there are heterogeneous agents in the same airspace, the first thing the first capability the agent should be equipped with is to infer what kind of type of vehicle dynamics the other opponent vehicles follow. And based on that, it has to evaluate its safety mechanism. So the crucial message here is that control theory is really, really helpful to think about how the dynamics affect our safety decisions. So as I showed you earlier, in this air taxi example, because the dynamics cannot allow the vehicle to hover, that's why this vehicle have to do deconfliction by doing this turnaround, right? So it's really important that all these vehicles are equipped with how they process dynamics, reasoning of dynamics to evaluate the safety actions of for its own and for these other vehicles' actions. So that would be my answer. And the second question was specific reward engineering required for the second approach? I think RL approach would take quite reward engineering. Also, can the operation be decentralized while using GNN? So the GNN is actually used to decentralize to provide the decentralized framework for multi-agent RL. So every agent makes their own decision based on only their own observation. It doesn't use any other observation. Yeah. But for the reward engineering, I agree that it does require some reward engineering. And also, when we engineer the penalty term that captures this potential conflict zone, we also had to try a variety of design for this reward. So definitely reward engineering is an open question for this reinforcement learning approaches. Yep. And question from Ingyu. In the multi-agent RL part, isn't avoiding the potential conflict region another collision avoidance problem with respect to bigger obstacle? Yeah, that's a really good question. So yeah, you're totally right. So if you consider this potential conflict region as a new safety constraint, then again, there will be leaky corner issue with respect to this potential conflict region. So that causes another layer of conflicts. So that is why actually in our framework, we treated this as a soft constraint rather than a hard constraint. Because if we treat it as a hard constraint, we'll have another dilemma of how we resolve such conflicts, right? Yeah, so that is a very good catch. It's a very important kind of limitation of this work. And I'm done with the questions in the Zoom chat. So, please feel free to ask more questions.
Any other questions? Well, actually, I'm new to this area, so I had some difficulty understanding some jargons, but
yeah, sorry about that.
yeah.
Yeah, I know that this talk is a little bit technical. Yeah.
I mean, we are, most of the people here are, pure data scientists,
I see.
And
Yeah.
so anyway, I'm surprised to see more, many questions coming. I have some questions. Maybe this may be because I don't know this area very well, but I know it's getting more important to, the combining the AI with the physical world is getting more and more important. So this is one of the problems that we are facing. But I recently met the people, actually CTO of a company called the Shield AI. Have you heard about the company?
Yeah, I've heard about it.
Yes,
Yep.
here in your scenario, everybody behaves reasonably, and with in a way, with a friendly thinking. But in the Shield AI, they're assuming that you attack somebody,
Yeah, I know.
So
Yeah. So
so in a way, think about it, even in this scenario, assume that you have some terrorist, flying many drones in the sky and chasing you. So how does it change the problem?
Yeah, that's a very good question. Actually, I have one agent here. If you look closely, one agent, I'm marking it as an adversarial agent. So this red agent is like, some adversarial agent that these other vehicles have to avoid from. So actually, the nice thing about the reachability framework I showed you today, it can be formulated also for non-cooperative case. Like, for example, we can add adversarial agent to our dynamics. And now that becomes a game problem instead of an optimal control problem. So in this game problem, we can verify, again, if we compute our reachability, we can compute the region from which our agent can win the other agent, meaning in terms of safety, we can still guarantee safety despite the adversarial actions of these other agents. So I would say these frameworks can also extend to such non-cooperative or adversarial settings.
Okay, so I mean the Shield AI developed the layer or the mission layer. So they assume they have a different hardware for different drones or different for example F-16 or F whatever and then they put this navigation layer and their current value is 5+ billion. They grew the value in 8 years. But I think it's just a software layer. So if you I mean they started developing this from 8 years ago. Now things have changed a lot. AI had a paradigm shift. So it might be a good idea to develop that kind of autopilot, auto-fighting, layer.
Yeah, I mean, in the defense application, this is actually already well kind of established or developed kind of business idea, as you mentioned, like Shield AI, Anduril, like I think even Palantir, a lot of companies are actually working on using AI to make automated operational decisions, mission, decision, things like that, even all the way down to the vehicle level control, right? So I totally agree that, these are already in some sense, in some form, being developed by these companies. But, like especially in the defense application, nobody care much about safety for each vehicle, right? Because vehicles are usually unmanned. They can risk safety to achieve a better rate of mission success. So I feel like safety is not the main concern for such companies. And safety would be a much more concern for the advanced mobility solutions, air mobility solutions for the public or for the general public. Yeah.
I mean, safety is a lot harder problem than just attacking
Yeah, exactly. But also another
attacking
thing
some
is,
enemies.
yeah,
so
another thing is, maybe I just want to mention this because it's a little bit funny. The reachability problem I showed you earlier in my introduction, if you flip the max to min, that becomes like a attacking problem instead of a defense problem. So again,
okay.
like reachability problem can also be used for such defense application. It's just that personally, I don't show such work because I'm, against using the reachability framework for such defense application. But I think it's reachability is much more valuable for these safety problems.
Okay.
Yeah.
Now there's one more question, I think.
So the question is, I heard that aviation industry used advanced computing system for more than 50 years, and numerous flight tests guarantees the safety. However, I felt that you usually target VTOL aircraft in destination. Is the aviation computer system in VTOL less developed? I don't think it's more about the computing system. It's more about the safety framework. So I agree that a lot of the existing framework guarantees safety for conventional airliners, but how they provide safety is by only operating the vehicle in a very, very conservative operational envelope. So this vehicle, like airliners, although the vehicle is much more capable, for safety reason, they only operate in a very, very conservative region. And it's because they don't have a constructive framework that can expand their envelope more efficiently. And also, they don't have a good framework that bringing in the information of the dynamics. So usually they only know whether the vehicle will be safe or not when the vehicle is close to a region where the dynamics can be linearized. Because people use linear model, using linear model for safety analysis is much easier. Yeah, so I would say definitely there are like decades of work in aviation community for safety for airliners, conventional vehicles. The main strategy is they allow vehicle to only work in a very, very conservative operational region.
I guess I want to share the information that I just got last week from the CTO of Shield AI. So the onboard computers, they use NVIDIA's edge chips. So they may be good enough for most of the applications.
Yeah, I think it's a really powerful compute for all these AI decisions.
Okay, now I think
more briefly, I mean, yeah. I mean, again, like another thing about safety is guaranteeing just safety is not the end of the story, right? Because you can always guarantee safety by making the behavior really, really conservative. The vehicle, like the eVTOL vehicle, can be safe by just doing only hovering. So the main aspect of safety problem is how can we ensure that the vehicle achieves tasks and have good performance while guaranteeing safety? So in that sense, what I really want to achieve is allowing the vehicle to have more control authority and use its full kind of capability when doing their missions, but doing so while guaranteeing safety.
Okay, now I think it's time to wrap up, and thank you for your great presentation.